Okay. Hello, everyone. Thanks for having me here. My name is Pietro, but in the internet, I go by Sweet Pete. I'm a penetration tester, security researcher, things breaker at a company in Italy named Shielder. In Shielder, we have research time slots, and in the past year, I've been spending my research time slots on Apple operating system, on specifically DYLD Surface, and this research is part of it. It's about the application Sandbox, so let's dive right into it. So this Sandbox in macOS, I would assume most of you are already comfortable with the concept of what a sandbox is, and in general in macOS it's very similar. So essentially a sandbox is a container for application. It limits what application can do in your operating systems, so that in order for the application to have access to files, networking, like your camera, hardware, the access must be declaratively, explicitly requested. In macOS, the sandbox, it's opt-in, like it's not mandatory. Application developer can enable the sandbox as a protection on their applications with a specific entitlement. And then they have to specify entitlements for the specific access that they want, like access for the camera, entitlement, access for networking, and so on and so forth. Actually, I told you that it's not mandatory in the sandbox, but that is not entirely true because it's highly recommended, and in some cases, it is mandatory. For instance, if you ever want to submit your application in the Mac official App Store, you will have to sign your application with the sandboxing entitlement, which gave me an interesting third model, I believe. On one side, we have the official App Store for macOS, where applications need to be sandboxed. On the other side, you have end users. Well, end users will typically have this thing that when running sandboxed applications, there is this sense of higher security when applications are running in an isolated sandboxed environment. I mean, this is why we reverse engineering malware in VMs, right? Because we trust the isolation. So what if we can produce an application that on paper it's perfectly sandboxed, but then when executed by the users will actually run unsandboxed and be mostly free to roam the system. So this is the goal. And we will see that it's doable, and I'm afraid there's no cool memory corruption in the kernel for this. You can all do it by leveraging a chain of, I would call them insecure designs, which is why it's definitely harder to fix, because insecure design, as you know, is one of the hardest bug kind to fix, because you have to rework entire pieces of code. So in order to understand what the technique into play here, first let me introduce the guest of honor, DYLD. It's the dynamic linking loader for OS X systems. So it's just the job of a loader. So when you run any kind of application in macOS, the control of execution doesn't go directly to your main, your application binary. First, it's DYLD that starts. DYLD will parse your macro binary. It will look all the dependencies, libraries, frameworks, stuff like that. It will load every library. For every library, it will run initialization code. And then at the end of this process and other things that DYLD does, the control will go to your main function. But then, what's the relationship between DYLD and the sandbox in macOS? This overcomplicated diagram that I don't want you to look too hard, it's just the call tree of how the sandbox is initialized in macOS. So the initialization of the sandbox happens inside the initialization code of libsystem.b, which is a system library. So basically what happens is that this initialization code will check your entitlements, and if the sandbox entitlement is there, the process will be sandboxed. Now, this is very interesting, right? Because, the consequence here is that in macOS, every application will start unsandboxed. And then the sandbox will be enabled in userland by initialization code loaded by DYLD. And this happens in this libsystem, which is a system library. And if you compile any kind of application in macOS, that dependency is appended. It's something that it's automatically appended, so DYLD will load it, will run the initialization, and by the time your application reaches your main, the sandbox will be enabled. we can immediately come up with a naive solution to bypass the sandbox then. Like, we are in control of the app, we can compile it, then we have the application, we can remove the dependency on the sandbox, on the libsystem library, and then we have a library, a binary, that will not load the libsystem library, and therefore, there is no sandbox initialization. The binary is free to run unsandbox. Yeah, this will not work. Like, DYLD has a lots of checks in its code, and when loading libraries, it will always expect to find these two guys here, libDYLD and libsystem. Like, these two libraries need to be there in order for DYLD to continue and do not abort. So we need to come up with a better plan. We will use a technique that, I just named it bypass via substitution. The idea is to leverage DYLD environment variables. So you can pass specific environment variables to DYLD to customize the way it works. You can increase the logging levels. You can interpose library, as Lars showed with DYLD insert libraries. There are many environment variables that are documented. So when I auditing this code, I stumbled upon this interesting variable. It's DYLD shared region. It's basically a variable to instruct DYLD on how to load system libraries from the shared cache. Its value can be either use or private. Well, yes, but actually not. I audited the DYLD code, and I found this other supported value, undocumented, namely avoid. So I wondered, what does avoid does here? And instead of looking immediately at all the code, I just wanted to test it in a binary. See what happens. If we run the binary as it is, like vanilla, it will just print hello world. As soon as we run it with this environment variable set to avoid, it's crashing. Main is not loading. And this is because it cannot find the libsystem library from the system cache. So what's happening here, actually, is that by setting the DYLD shared region to avoid, we're basically avoiding loading libraries from the shared cache on disk. So DYLD cannot find any of the libraries it wants. We look at another environment variable here. It's DYLD fallback library path. This is very simple how it works. It's basically a way to instruct DYLD. If you cannot find libraries wherever you have looked, I give you a fallback path where you can search for libraries. So if we combine the avoid environment variable to the fallback library path, you see that, again, the binary is crashing, but now DYLD is searching in our custom path for the libsystem library. So this gives us a better and still very simple plan on how to bypass the sandbox here. So we can, first of all, compile our own replacement libraries for libsystem and libDYLD. Just that in libsystem, we avoid all the sandbox initialization code. We just use kind of a stubbed libraries, which still needs to be well-crafted enough so that DYLD will find the structures that it's looking for in the libraries, but no sandbox. Then we run the binary with the two environment variables, DYLD shared region to avoid loading the on-disk cache, and DYLD fallback library path to point at the path where our custom replacement libraries live. By doing this way, DYLD will find the two libraries, but no sandbox will ever be executed. So in order to test this, we can just use a simple reverse shell that connects to localhost on port 4444. Using a reverse shell is a good way to test the sandbox because in its normal state, unless you explicitly request access to networking, this should crash. Because in a sandbox, without explicitly asking for networking, you cannot just connect and send a reverse shell wherever. In fact, we see that if we run the reverse shell as it is, the binary will crash, and we will start seeing logs from the sandbox, like deny. We don't want this connection going outside for 4444. So good job, sandbox. That's what you should do, right? But see what happens if we run again the binary, but this time we're supplying our two environment variables, and we have our raw GU replacement libraries, no complaints from the sandbox at all, and we get our local list, we get our reverse shell, and it's unsandboxed. So the way it is right now, it kind of works, but it feels like an experiment, doesn't it? Because, I mean, remember the goal was to have a package that we can eventually submit to the App Store, that we can distribute. This looks like an experiment. Like, we cannot expect users like running our application with custom libraries and environment variables. That feels shady. So we need to think more and find out a way to actually package in a neat way our binary. We mainly have two problems that we want to solve here. First one is that we need a way to supply on launch the DYLD environment variables automatically. We don't want the user to supply those variables. We need the binary to automatically launch with those environment variables. Well, luckily, or unfortunately, this is quite easy for an application because launch services, which is the service that handles launching applications when you double-click on them or when you open them in macOS, supports in the info.plist file for the application a specific key named ls environment where you can set up whatever environment variable that you want, and it will be automatically attached to the expanded in the environment of the application when the application runs. On the other side, there's another problem that we want to solve, and that is notarization. If you ever used a macOS, you're used to this kind of pop-up. This pop-up, it's something that you see when you're running a notarized application. So it's basically a way for Apple to to have your app, even if it's distributed outside the official App Store. With notarization, Apple can still check it and can still tell users, OK, this is distributed outside of the App Store, but Apple checked it for malicious software and none was detected. So you can just, like, if you want, click open and you will open it. If we don't have notarization, executing applications signed by someone else in macOS will get really hard. You will have to jump hoops and go specifically in the directory where the application is, right-click, open, and that's not something that we want. We want the easiest distribution that we can. Now, the little problem with notarization, with this kind of bypasses, though, is that in order for notarization to be enabled, you need a specific protection named hardened runtime. So the hardened runtime is a protection that developers can enable on their application, and it protects the application from many kinds of code injection, like loading unsigned code or mapping RWX segments in the memory of the application. And that includes setting DYLD environment variables. So if we want to notarize and we need to enable hardened runtime, we lose the capability to have DYLD environment variables, which would mean it's a game over for the chain. Well, however, actually it isn't. In fact, the environment in macOS, compared to, for example, what we see in iOS, is very flexible. Instead, in fact, the hardened runtime, even when enabled, supports many entitlements that you can use to relax the requirements of the hardened runtime. So by using this specific entitlement, you can still enable the hardened runtime, but allowing the DYLD environment variables. So the only thing that we need to do to have notarization and enable the hardened runtime is supplying this entitlement. And I'm going to tell you, when I found out about this, my first thought was, OK, this entitlement exists, but no way by setting it, I will be able to notarize the application or submit to the App Store. This probably, for sure, is checked by Apple, and no application will be trusted with that entitlement. So I did what every healthy mind here would do. So I took 2 weeks of my time. I wrote a tool to automatically scrape, download, install, and scan applications from the App Store. That tool is a separate story, but reversing the App Store internals was fun. And I found out that in the App Store, there are many applications compiled with that entitlement, and even very popular ones. And there are other entitlements there. So what this gives us is that definitely that entitlement is not going to be a problem if we want to distribute our applications. So I think it's time for a demo now. I will show you a video. This video is actually very simple. It shows you the end product. The end product is a user which takes this application, checks for like security properties. It checks that application is valid, signed, notarized, and that the sandbox is enabled. But then once the user double-clicks on the application, the reverse shell will start showing that the application actually ran unsandboxed. OK. So we start the reverse shell listener. You probably have seen the DMG distribution technique for applications. It's commonplace for distributing outside the App Store. We get the signing info, signed, notarized, very trusted. We see that it's sandboxed. And we are like security-savvy users, but we install it because it's sandboxed and doesn't request any special access. As soon as we double-click, that's the reverse shell, which means that the application executed unsandboxed. OK. So jumping to conclusions here, the fact that in macOS the sandbox is applied in user land is an insecure design. Like, you cannot really trust the sandbox because there are so many things that could happen in user land that are out of control of the system that this cannot be really trusted. Now, it's true. Many people will tell you that the sandbox is opt-in, so it's not mandatory. So it's not a big problem that applications can escape it, because there are other systems like TCC, transparency, consent, control in macOS, that instead are enforced. However, unsandboxed apps in macOS still have lots of access. For instance, they can access your downloads folder, and I mean, of course, no one ever has sensitive files in their downloads folder, right? DYLD is a well-known target for bypasses. There are other documented techniques. There's one via DYLD interposing. After reporting that by interposing, like Apple apparently checks for it when submitting to the App Store. Well, all the things that concern the App Store are quite undocumented because we don't really know what checks are performed, what checks are manual, what checks are automated. So unless you start submitting to the App Store, it's really hard to tell. As a bonus update, I've reported all of this chain and all of the packaging thing to Apple. And in September, like latest DYLD commit, they have patched away the avoid variable. It's now supported only in the OS simulator, which practically makes it useless for our use case. And I guess that's it. Thank you.